Thank you, Chairperson. Good morning, all the audience who are attending in this session. My name is James Sakampat. I come from Leicester University, Tasmania Province, England. I feel honored to propose our paper entitled Correct Controlling the Same Feedback Loop. Outline of this presentation consists of introduction, materials and method, experimental results and description, final view, conclusion. Introduction. The measurement of flow is very important in industrial applications, optimum performance of many processes requires specific storage. The cost of many routes and processes is based on the measured flow for a pipeline. That is necessary to accurately measure and control the rate of flow for accounting purposes. In the measurement and control system, when a change in a measured variable with respect to a reference has been sensed, it is necessary to apply a control signal to an actuator to make corrections to an input control variable to bring the measured variable back to its previous value, such as a mixing of two liquids as shown in the left figure, which control the flow rate of liquid B to be proportional to the flow rate of liquid A. In most cases, any change in the variables such as temperature, pressure, mixing ingredients, and level can be corrected by controlling flow rate. The right figure illustrates the water meter system that controls water temperature by controlling the stream flow. Originally, the flow rate control can be achieved by an analog feedback system in which any change in flow rate is sensed and compared with a fixed reference voltage. The error voltage is amplified by the amplifier, whose output state guides the actuator. However, this analog feedback system is not satisfactory in some equations, where excellent speed regulation and fast dynamic response are required. These features can be achieved by using a phase-lock loop control system. This section is materials and methods. This section consists of phase-lock loop, flow sensor connected DC pump, and the process circuit. The basic functional components of a phase-lock loop are voltage control oscillator or VCO, a phase detector, and a loop filter. The visual oscillator and angular frequency omega 2, which is determined by the output signal Vs of the loop filter. The angular frequency omega 2 is given by equation 1, where omega 0 is the center frequency of the VCO and K0 is the VCO gain. The phase detector compares the phase of the output signal with the phase of the reference signal and generates an output signal Vd. The output signal Vd consists of a DC component and a high-frequency AC component. Since the latter is undecided, it is cancelled by the loop filter. In general, the output of the loop filter is approximately proportional to the phase error. theta E. The former is given by equation 2, which theta E is equals to 0, which Kf represents the gain of the loop filter. Assuming the angular frequency of the input signal V1 is equal to the center frequency omega c, the VCO operates at its center frequency omega 0. The phase error is 0, indicating the output signal of the loop filter Vf is also 0. If the phase error theta E was not initially 0, the phase delay would develop a non-zero output signal Vd. After some delay, the loop filter would also produce a finished signal Vf because the VCO to change its operating frequency in such a way that the phase error finally vanishes, and after some second time, the VCO will oscillate at a frequency that is exactly the frequency of the input signal. Note that Vf is equal to 0 if V1 and V2 are in phase, and it reaches the maximum value Vdd when the two signals are exactly out of phase. The relationship between the phase error and the output voltage of the loop filter is illustrated by a curve in the bottom picture. An example of forward sensor is the turbine flow meter. As shown in this picture, the turbine rotor is mounted in the center of the pipe and rotates at a speed proportional to the rate of flow of the fluid passing over the blast. The turbine blasts are normally made of a magnetic material or ferrite particle in plastic so that they are unaffected by corrosive liquids. As the blast rotates, they can be sensed by a home device attached to the pipe. But the signal generated by home sensor has a frequency proportional to the flow of liquid. The turbine should be fully used with clean fluids such as gasoline. If a DC pump is connected together with the flow rate sensor by the pipe, as shown in this picture, then it can be considered as a VCO, which the voltage at the input of the pump determines the frequency of the output of flow sensor. A relationship between the flow rate and the input voltage Vin of the pump can be considered as equation 3, where Kp is the pump gain and A is constant. A relationship between the angular frequency of the output signal of the flow sensor and the flow rate can be considered as equation 4, where Ks is the gain of the flow sensor and B is constant. Substitution of equation 3 in equation 4 gives equation 5. It is easy to see that equation 5 corresponds to equation 1 as listed above. An example of liquid used in this table is water. In order to control flow of water through the water hose by using circuit resistance phase loop, it is important that the phase of output signal of flow sensor must be synchronized with every second of the controlling signal. Fifth synchronization property of the fetch lock loop. The purpose circuit is therefore insensitive to varying of the load, based on the discrete principle of controlling coded. Block diagram of the purpose circuit can be depicted in this figure. The reference signal V1 from generator is connected to the one of the two inputs of the phase detector on the CMOS 4046 chip. The phase detector is simple and excessive for logic gate. The output VD of the phase detector is filtered by a low-pass filter. Here, the loop filter is a simple passive RC filter. From the principle of the phase lock loop, the VCO implemented by combination of DC pump and the flow sensor must be running at frequency omega 0 when there is no difference between phase of the phase signal and of the VCO output. That is, the control voltage VF is 0. In order to do this, a summing amplifier is used to add DC signal to the filter output VF, and then its output is amplified by a power amplifier whose output drives DC pump. Next, the output signal of the flow sensor is connected to the input of frequency divider on the 4040 chip, whose output is connected to the other one of inputs of the phase detector. The frequency divider that is employed within the loop reduces the frequency difference. Here, a frequency divider by 2 is designed. In this paper, the VCO system is built and tested. It consists of a mini DC pump, 12 volts, 7 liters per minute, and water flow sensor by FG21. In the datasheet of this flow sensor, it depicts that flow rate can be calculated gradually by the equation Q equal to the frequency at the output signal of the flow sensor divided by 7.5, where Q is the flow rate in liters per minute. Here, the VCO is implemented by combination of short DC pump and flow sensor, as illustrated in the left picture. The relationship between the voltage at input of short VCO and the frequency of its output signal is represented by a curve as shown in the right picture. Note that the frequency is proportional to input voltage. To verify the purposes principle, the laboratory experiment of the purposes circuit is set up as shown in this picture. In the experiment, the frequency of the reference input signal is 4 Hz. That is, the required flow rate is about 1 liter per minute. First, in the lock state, we set the phase error to be small as possible as when the free edge of the hose is minimum. Then, the load active on the system can be easily varied by reaching the free end of the water hose up vertically in the air, which is divided into different levels. The first level is lower than the second one, but in each level, the frequency of the output of the VCO remains the same as that of the reference input, namely 4 Hz. The obtained signal from the experiment are shown in the left and the right pictures. In each picture, the upper track is reference input signal. Second track is the output signal of the frequency divider that implies the output signal of the VCO. The third track is the output of phase detector, and the last track is the output signal of the low pass filter. Note that when the free end of the water hose is reset higher than usual, the duty cycle of the output of phase detector increases and the voltage output of the loop filter also increases, which is amplified to drive the pump. As a result, the frequency of the output of VCO, that is divided by 2, remains the same as that of the reference input, that is, the voltage of the water does not change. From this experiment, it illustrated that the system is stable to perturbation. In this article, voltage controlling by using feedback loop has been proposed. The main advantage of the proposed circuit is that the voltage is stable to perturbation due to synchronization property of the feedback loop. The experimental results have illustrated that the proposed principle can be applied for controlling voltage. Thank you.